Hello, my name is Roy Simpson, Professor of Mathematics at Customers River College in Sacramento, California. In this video, we continue our discussions on Taylor-Maclaurin series, and specifically, we're going to talk about how to multiply two Maclaurin series together to derive the value or the Maclaurin series for a function that is the product of two functions. So often when you do this, and then you have to do this in a course like differential equations, when you do this, given two functions who are both not polynomials and you're trying to find their product as a power series, you just can't find a pattern to it. It's very challenging to find a pattern if there is one that even exists. And so because of that, we only require that you write out maybe the first 3, 4, or 5 non-zero terms of the expansion. You rely upon technology, honestly, to write out as many terms as you need. So in this case, we're going to recall a couple power series expansions, e to the x. Its Maclaurin series is n equals 0 to infinity of x to the n over n factorial. And cosine of x, being the even function of the two kind of major trig functions, is going to be the sum of even powers of x. So, and it's an alternating series, so negative 1 to the n, x to the 2n, and then we have over the quantity 2n factorial. So, given that we know those two Maclaurin series, and we know that those are convergent to those two Maclaurin series, so they're actually equal, we're going to go ahead and rewrite that e to the negative x squared as a summation. Let's see, so let me write f of x first. F of x, which is e to the negative x squared times the cosine of x, can now be written as a summation n equals 0 to infinity. And then we have, instead of an x to the n, we have a negative x squared to the n over n factorial. And we're going to multiply that by a summation n equals 0 to infinity. Again, alternating sequence, negative 1 to the n, x to the 2n, or alternating series, sorry, over 2n factorial. And you should have learned this early on with series, but the product of two series, just as an aside here, so let me move this over to the side. You should have learned a long time ago that given two series, an and bn, when you try to find the product of their sums, it is not equal to the series an, bn. And that's because if you were to say it is equal to the series an, bn, you're actually multiplying first terms of each together only, the second terms of each together only, and the third terms of each together only, and so on and so forth. But in reality, you'll see that this is actually a huge distribution process, and it's pretty much impossible. Let me write the equal sign a little bit more to the left. It's pretty much impossible to find a nice pattern for that. So let's see, when n is equal to 0, and normally I would write this, by the way, this first series as negative 1 to the nth x to the 2n, but because I'm expanding that out, I'm not going to bother with that. When n is equal to 0, I have who cares to the 0th power over 0 factorial, which is 1. And then when n is equal to 1, I get a negative, and then x squared over 1 factorial. And when n is equal to 2, I get, let's see, positive x to the 4th over 2 factorial. And a negative, you can see the pattern already, x to the 6th over 3 factorial. And a positive x to the 8th over 4 factorial. And I think that's good. I might just write one more out, x to the 10th over 5 factorial. And we're going to multiply that by the expansion for the cosine, which when n is equal to 0, everything's 1. When n is equal to 1, you get a negative x squared over 2 factorial. And then when n is equal to 2, you get a positive x to the fourth over 4 factorial, and you can see that pattern will continue. So I'm just going to write it out a few more. I should probably just stop at x to the 8th. Now remember, in the question, it asks us to find the first 3 non-zero terms. So all you need to do here, and this is what you're going to do in maybe differential equations, is first of all, find the constant term. And in fact, maybe I should, as down below a little bit, I'll leave enough room that we can actually see what we're doing, but I'll say, okay, what's the coefficient of x to the 0th? In other words, what's a constant? And if you take a look at anything that creates a constant here, you have this 1, and it's going to distribute to everything over in the second factor here. Well, the only piece that gives me a constant is 1 times 1. So I can go ahead and write here that we have 1 as our constant term, and let me erase those highlights. And now let's say what the coefficient of x to the first is. And again, I'm going to start with the 1. What does 1 have to multiply against on the second factor to get me to x to the first? Nothing. If that 1 multiplies anything over there, it's going to be a second power. So let's move forward, and you'll see that the next term in this increasing ordered power sequence here, the next term is going to be x squared. Well, there's nothing over on the right-hand side that I can multiply by x squared to get x to the first. So you can see that the coefficient of x here is just 0. Let's talk about the coefficient of x squared, though. Now, that's the interesting one. I'll take this 1 again, and I'll multiply it. Well, multiplying against the 1 on this side is not going to give me an x squared, but multiplying it by this negative x squared over 2 factorial, yep, that will give me an x squared. So I'll go ahead and say, let's see, 1 times a negative x squared over 2 factorial. So that means I have a negative 1 over 2 factorial of those x squareds. And then also, I'll use a different highlighting color. If I take the next term in line, a negative x squared over 1 factorial, and multiply it by this 1, I will also have an x squared. So let me go ahead and say I also have a negative, or I have a 1 times a negative 1 over 1 factorial of those x squareds from the blue ink. And you could, probably should in this case, honestly, simplify this arithmetic. That's just negative 1/2 minus 1, or negative 3/2. And so I'm going to go ahead and remove my highlighting now. That's why I'm highlighting low, so I can easily erase it. And then I'll go back here and I'll say, well, what about the x cubed? Now, I can easily see there's not going to be an x cubed coefficient, so that's 0. And then I'll worry about x to the fourth. Now, how are you going to get an x to the fourth? There's going to be a lot of highlighting here. This 1 can multiply this positive x to the fourth over 4 factorial. And this negative x squared over 1 can multiply this negative x squared over 2 factorial. And finally, this positive x to the fourth over 2 factorial can multiply this 1. That's how I can get x to the fourth. So let's go ahead and look at those coefficients. In yellow, I have 1 times 1 over 4 factorial, or in other words, just 1 over 4 factorial of those x to the fourths. In blue, I have a negative 1 times a negative 1/2, or in other words, a positive 1/2, or 1 over 2 factorial of those x to the fourths. And then in green, I have another positive 1 over 2 factorial. Now let me just check my work really quickly. That is absolutely true. Okay. And here again, you can simplify this down. Let's see, 1/2 plus 1/2, that's going to be 1. And then 1 over 4 factorial, that's 1 over 6 times 4 is 24, 1/24. So this is going to be 25 24ths when everything is simplified. I'll go ahead and erase my highlighting. All right. And since I only want the first 3 non-zero terms of this expansion, I'll go ahead and write, this is approximately equal to. It's not actually equal to, it's just approximately equal to. Let's see. So the coefficient of x to the 0th, which is 1, is 1. The coefficient of x squared is a negative 3/2. And then the coefficient of x to the 4th is a positive 25/24. Now again, some people will say that this is equal. It's not, but they'll say it's equal, and then they'll just say plus ... The problem is the plus ... means that there should be a pattern that you can somehow derive. And in this case, there's just not a pattern that we can derive. So I'm going to just, because we're approximating using the first three terms, I'm going to say this is approximately equal to, using the first three terms, this polynomial. So anyway, that's how you go through and find the product, or find a power series representation for the product of two functions, is that you look at their power series separately and you multiply out term by term. And there's no way that in general you can find a pattern. So I hope that's helpful to you. And yeah, please watch the next video online.